Okay, we'll go ahead and get started. I have posted your second homework assignment on CCLE, okay? And there's two parts to it. The first is textbook problems, okay? And there's about there's about 5 of those or so. And so you'll go to the textbook, you'll answer those questions, you'll render your answers into a HTML. You'll put it in the R Markdown folder file, render them as HTML, and you'll upload your HTML file. Okay. The other part is the tic-tac-toe script. Okay. The tic-tac-toe script, you will produce an R script, and you will upload the R script over here. And then the way we're going to grade the tic-tac-toe assignment is the graders are going to download it, and they're going to try to execute it and play a game, okay? And so it's your responsibility to make sure the game will run properly with a completely empty starting environment, right? So if you reference objects like this list of triples or something in your script, don't assume that exists in the environment, okay? The environment will always be starting empty. So anyway, so you have that. I've written some recommendations, okay? Because I wrote a solution that will play tic-tac-toe myself on my own computer, and so I just thought about how do I break down the program into smaller functions, and I wrote that just kind of my ideas in the tic-tac-toe recommendations. You are not required to obey my recommendations. They're just recommendations, okay? But for many of you, okay, well, for some of you guys have been coding for a long time, and writing tic-tac-toe is not a big deal, okay? But for others of you, Stats 20 was your first ever coding class, and this is kind of going to be your first coding assignment where you probably have to write over 100 lines of code, okay? And if that's the case, the challenge could feel a little bit overwhelming at first, but it's not, okay? And so I've tried to break it down into smaller, manageable chunks, okay? The homework 2 is due a week from Monday, so that gives you 2 full weekends to work on it, okay? So you can work on it this week and work on it next weekend, and that should be plenty of time to complete it, okay? Please, if you're relatively new to coding, please get started on it right away, all right? Look at the recommendations, see if you can start off, start by creating your display function, okay? You can accomplish that in like 4 lines of code. It's not too terrible. All right, I don't know, 6 lines, I don't know. It's a simple thing, but you have to start thinking in terms of functions. And so get started on it. If you wait until next Friday to begin, you will not have a good time, okay? So please take a look and try to get started on the assignment. Okay, are there any questions on this? There's 2 parts to homework 2, the textbook problems and the tic-tac-toe coding. The textbook problems, the textbook is available, should be free for all students as long as you're connected to the UCLA network. So you can either download the textbook while you're on campus right now, or if you're in student housing, then you'll have access to it. But if you live in an off-campus apartment or something, you need to connect to the UCLA VPN, okay? And then you'll have access to it, okay? Any questions? All right, we're good? Okay, then let's take a look at today's lecture. All right, and again, respond to the online poll if you haven't done so already. Looks like most of you guys have. All right, so we'll talk flow control and functions, and I think we've started already talking about loops. Okay, so the for loop, probably the most common thing is to say, for x in 1 through 10 or something, some kind of integer vector. But a for loop will run over any kind of vector. The vector can be a list, it can be a character vector, it can be anything. And when you do a for loop, it will just iterate over the vector. When you run loops and you want to store the results, okay, it's you can use the index. Like if you're using an integer vector, you can use x as the index and store your results in the position according to the index here. Okay, so in this case, x is going to take on the values 1 through 10. You're going to store the result of x squared into the results vector in position x. So when x is 1, 1 squared goes into the first position. When x is 2, 2 squared goes into the second position, so on and so forth. Okay. Here's just a recommendation that you should create the vector first with all this stuff, and then you just fill it out. It's better than copying the vector and combining it. It's better than not properly defining the size of the vector, and in this case, R needs to resize the vector every single time, your results vector. We have other types of loops, like other than the for loop, we have the while loop. Okay, and the while loop is very useful because it will run forever until a condition is no longer met. So if this condition turns false, that's when the while loop stops. So here we start off with I is 1, and we're going to store the result I squared into results position I. Okay, so when I is 1, 1 squared goes into results position 1. And then it increments I plus 1. It says I plus 1 is I. So I is now the value 2. It checks the condition. Is 2 less than 10? Yes. 2 squared gets stored into results position 2. Increment I to 3, so on and so forth. So it'll just keep running and running and running until this is no longer true. So, I will be 10. 10 plus 1 becomes 11, and when I becomes 11, this is false and it quits. Okay. So when you write your tic-tac-toe program, you're probably going to use a while loop. Okay. It's gonna keep running until some condition is no longer met, and that condition will probably be while, you're gonna have to figure out how to write this, but while there is no winner, keep playing, right? So while there is no winner, keep playing the game, and then finally, once a winner has been declared, the while statement will become false and the game will quit, all right? And so you'll need a while loop, because a tic-tac-toe game can be completed in as little as 5 turns, right? Because player 1 needs to get 3 in a row, so a tic-tac-toe game can be completed in as little as 5 turns. It might take as many as 9 turns to end the game, okay? Because there's 9 total positions. So you can't use a for loop which says, keep going until however many turns have been taken. You need something that says, while there's no winner, keep playing. When there is a winner, stop. If this statement is always true, the while loop will run forever. So if you set something up wrong and this statement is always true, or if you just write while true, it's going to just run forever. Okay? And that's basically what a repeat loop is. Okay? A repeat loop is basically while true, meaning this is going to just keep running forever. And the way you stop a repeat loop or a while true loop, you need to run into this statement called break. And break will quit the loop. Okay? So no matter whatever it's doing, if it encounters a break statement, it will quit the loop. So this loop, the while I less than or equal to 10, and this repeat, they are equivalent in that this will keep running until this statement is no longer true, and this will keep running until this if statement is true and the break loop is executed. Okay, so it increments, and you know, when I is 1, 2, or 3, this statement, if I greater than 10 is false, so the break is not executed. But then once I reaches 11, at I equal to 11, this statement is true, and it does execute the break. And when it reaches the break, it stops. And so we get this. Is that okay? So the word break is a special keyword, and the word next is another special keyword, okay? So break will always end the current innermost loop, okay? So if you got a loop inside a loop, it's just going to end the one that's where the break is located, okay? And so so in this case, what break does is it quits the loop. So we're just running for I in 1 through 10, and then it's going to do if I mod 2 is equal to 0, meaning if I is even, execute break. Okay, so first I takes on the value 1. Okay, and then asks, is 1 divisible by 2? No, because the answer is no. This line is not executed, and it skips ahead, and it goes to cat I to the screen. So it's going to print 1 to the screen. It reaches the end, and it says, okay, we go back to the top of the loop. I now takes on the value 2. Okay, and it says 2, I is 2. Is 2 divisible by 2? Yes, this is true. So then it encounters the break statement, and it quits. Okay, it counters break, so it doesn't even execute this cat statement. Okay, as soon as it hits the break, it quits the loop, it quits all code. It's not going to cat 2 to the screen. It quits, and this is the end of our code. It printed 1. Okay, and if we ask the computer what is the value of I will take on the value 2. Here we have the exact same code. All right, the code is exactly the same. All I've done is I've changed the word break to the word next. What next does is it says, don't look at the rest of the code for this current iteration, just go immediately to the next iteration. Okay, so it says go straight to the next iteration, ignore the rest of the code. So it starts off with I is 1. Okay, this statement is not true. 1 is not divisible by 2, so it skips. Next is not executed, and it cats 1 to the screen. So 1 gets printed. Next loop begins, 2, okay? And it says if 2 is divisible by 2, that is true, and so next gets executed. So when the next gets executed, it goes back to the top of the loop, and I becomes 3. So it never cats 2 to the screen. 2 does not get cat to the screen. So it goes on and takes on the value 3. I is 3. 3 is not divisible by 2, so next is not executed, and it cats 3 to the screen. Then I becomes 4. 4 is divisible by 2, so next is executed. 4 is not cat to the screen, and it skips to the next loop and goes 5. And so what ends up printing is 1, 3, 5, 7, 9. All right, is that okay? So break will just quit and stop all code. It stops the loop entirely. Next, we'll continue the loop. It just skips to the next iteration. When we're talking about for loops, I think we said, you know, you can a for loop can iterate along any kind of vector. Okay, whether it's a numeric integer vector, which is probably the most common scenario, but it could be a list or whatever. And so earlier on, we had this thing where we list L is this list of 3 things, and we just wanted to say what is the length of Y, and it prints that out to the screen. Okay. Over here, instead of iterating along the elements of the list L, we might want to use the integers 1 through 3 as indexes, okay? And that's what sequence along L does. Sequence along L is actually equivalent to the vector 1, 2, 3, because L is a list of 3. It's going to create a vector 1, 2, 3. And so here, X now takes on the index 1 and index 2 and index 3. And so this is pretty equivalent, and so we would have to subset L to the first element. Okay, so we'd say L double square bracket 1, which will pull out the contents of the first element of L, which is this vector 1 through 3, and we say what's its length, and it says 3. And that gets stored into the results vector in position 1. Then X takes on the value 2, and we say what's in the second compartment of the list. It's a vector of the first 7 letters. We say what's the length of that? It's 7. We store that into position 2 in the results vector, and so on and so forth. Okay, so a for loop can iterate directly along a vector, okay, or a list or whatever it is, but sometimes it's handy to be using the index of those positions. And so sequence along works like that, okay? Sequence along is exactly equivalent, or in functionality, to using 1 colon length of L. So length of L is 3, okay? L has a length of 3, so it's basically writing 1 colon 3, and you get 1, 2, 3. Sequence along L basically does the same thing, 1, 2, 3. Sequence length of length L will also produce a sequence 1, 2, 3, okay? So these are all kind of equivalent things to getting like index positions. Is that okay? All of these things that we've done so far, they could be vectorized. And I don't know if you've heard, but R is not the most efficient programming language, okay? But we love it. As statisticians, we love it for a few reasons, okay? One is, it's relatively speaking, it's very easy to write code in R, okay? R is dynamically typed, and it's very forgiving. It will coerce things from one type to another. You can take means of logical vectors easily, and it has a lot of nice features, okay? In terms of being able to write a script easily and get it running, okay? The other part is that R has the built-in NA type, okay? Or not NA type, but just NA values for missing values, which is fairly unique to R and very important for statisticians, because whenever we collect data, there's many scenarios where we're not going to have complete data and we have missing things. And other languages don't have an NA for in the thing, okay? Python, notably, does not have NA. They have NaN, okay, not a number, but that's a little bit different, okay? And so so you have to handle things differently. So because of that, there's a few trade-offs, of having an interpreted dynamically typed language, is that it's not as efficient for certain things, right? C has a compiler that will make your code super efficient. It'll find these things and make them super efficient. And one thing is that in R, loops are slow, okay? And so, I'm gonna demonstrate something. Don't do this, but okay, so here I can just write a for loop, okay, and I'm going to say for I in 1 through 10 to the 7. Here, wait, let me just start off by saying x is 0, okay? And I'm going to say for I in 1 through 10 to the 7, store the value I squared, okay? So 10 to the 7 is 10 million, and we're going to just find the value of 10 squared. For everything, we're going to square these, okay? And you can note how long this will take my computer to run, okay? So it's running, it's got a lot of numbers to crunch through. Okay, and now it's done, okay? The vectorized operation, okay, much easier is just to do 1 through 10 through the 7, and just square it directly. Okay, so you can just vectorize this, and it was a lot faster, right? Okay, and so loops are much slower than vectorized code. Okay, but the key is it's probably easier to think of things as loops than it is to think of vectorized code, especially in certain situations. So first get it coded correctly as a loop, and then if you can think of ways to vectorize it, then worry about that. Okay, so so anyway, loops are inefficient, and if you're able to avoid them, then that's great. If you're not, it's okay. But just note that as far as R goes, loops aren't the quickest things. Okay. Functions. It's very, very important that we learn functions and that you get in the habit of writing functions. Okay. And I think later on I have a slide on when you should write functions. But functions are intended, and I'll add another slide, I think, in your notes, to just be able to do some chunk of code and repeat it in situations, and you can modify these things with different arguments. And so the rule of thumb is if you have a task and you need to do the task again, you might copy and paste it, okay? And if you copy and paste it once, that's okay, all right? And if you copy and paste it twice, so you're doing the same thing 3 times, you should start thinking about a loop, okay? And if you find yourself about to copy and paste the thing to do it a 3rd time, then you definitely need to write a loop, okay? So taking a piece of code, copying and pasting it, and running again, that's okay. Twice, that's when you should start thinking about writing a function. And then if you do it a 3rd time, you definitely need to write a function, okay? And so, for example, a common scenario is maybe you go to a website where you're going to download data, okay? But the website, for whatever reason, has decided to split up their data into things. And you got the data file for January 2018. And then you have the same data, but it's for February 2018. And then it's for March 2018. And then it's for, what's after March? April 2018, okay? And maybe for each of these things, there's a few things you need to do. Maybe you have to read in the CSV file, okay? That's fine. But then you need to also add a column that says January. And then, I don't know, maybe there's other things you need to like modify one of the columns so that you're changing it from, I don't know, you're going to split up the values into different categories or things like that, right? You can imagine there's a little bit of processing that you need to run on each data file, okay? And so maybe you've got like 5 or 6 lines of code. And then you say, okay, well, that worked for January, and so I want to do the exact same thing for February, all right? So you just take that chunk of code, you copy it, you paste it, and you say, all right, let's replace January with February. Let's make a couple changes here, and then we'll run it for the February file. And then you say, okay, well, here's March, right? So now you're going to copy and paste it again, and you're going to modify February to March and do this and that, okay? In that scenario, by the time you do the 3rd copy and paste, you need to be saying to yourself, this needs to be a function, okay? If you copy and paste it once, it's okay. Copy and paste it twice, you should start thinking of a function, maybe write a function. If you're doing it a 3rd time, it definitely needs to be a function. And the reason for that is maybe later on you realize, oh, you know what? I need to make a small change. I need to add another column to this file, okay? And if you did the copy and paste, then you need to redo the function. You need to make that modification in like all 12 locations for all the months of the year. And you don't want to do that, okay? You just want to make the modification one time in the function and then just rerun the function for each of the files, okay? And it's going to be much better, and you're going to be much less error prone than this bad habit of copying and pasting. Copying and pasting is the easiest because you got it working once and you just want to do the same thing, and our brains are easy are lazy and we just want to stick with that, okay? But if you're going to do it more than 2 times, it needs to be a function, and it just requires a few modifications to turn something into a function, okay? But the way a function works is we define it like this, okay? We say, here's the name of the function, and you tell R, I'm creating a function, okay? And then you give it some arguments, you write some code, and then the function ends with a return output, okay? You indicate to R that you've got a curly brace and a closing curly brace to kind of group all the lines of code together. On some of the slides, I don't write the curly braces because the function is only 1 line of code, okay? So if the function's only 1 line of code, just like the if statement, you don't need the curly braces, okay? Curly braces are used to group more than 1 line of code. But if the function's only 1 line of code, like here, then you don't need the curly brace. Okay. Here I've created a function f, and functions are just objects. So you can throw a function into some other thing like a list, okay? And the list will store the function, okay? If you ask the type of on a function, it will say it's a closure, which is a little bit strange, but functions are just objects, and don't worry about this slide, but you can have, a function will take inputs and it returns another object, and because functions themselves are objects, you can have a function return another function, okay? And that feels weird, but you can have a function return another function, and so that's something, but don't worry about that slide, okay? What a function does is it takes in an argument and it will return a value, okay? And so you can tell R to explicitly return it using the return statement, okay? Or if you don't use the return statement, the last line of code inside the function will be the value that's returned, okay? So here I'm saying take in the value x and do x times x and return that. All right. Over here, I say take in the value x, calculate x times x, and because this is the very last line of code inside the function, this is the value that's going to be returned. Okay. For example, if you ask R, what is the LM function? So, are you guys taking 101A right now? And have you created linear models with LM yet? Or you should have, okay? So when you call LM, this is the code that R is running, okay? You can actually see the code that R is running. And it says, take X and take Y and do all of this stuff, okay? And basically, it's producing a list called Z, okay? It's producing this list Z, and it's going to say things like, take the coefficients of this matrix and other stuff, okay? And then the very last line of this code for LM says Z, okay? And what that means is it's going to return the list Z. So that, if you take X is the values 1 through 10 and Y is R norm 10, right? Okay, and then I say LM X comma Y, whoops, not, I guess Y by X, and we call this model, or something like this, right? Model is the type of model is a list, okay? And if I do print.default on model, okay, we can see it's a list, okay? We can ask for the structure of the model, and it's a list. And anyway, all of this was all just produced inside this list Z, okay? And so the last line of the function is Z, and that's the value that gets returned, okay? So that's an implicit return there. Okay, the key thing about functions in R, okay, not other languages, but in R, a function is allowed to return only one object. Okay, you can only return one object and one object only. So if you want multiple things back, if you want multiple values back, you need to group them together into a single object. So let's say I want the values x, x squared, and x cubed. I can't return 3 things as 3 separate objects. I have to group them together into a single vector, okay, a single object like this. I use combine, and then I'll get all 3 values back, 2, 4, and 8. So if I run f on the value 2, I can get all 3 values back, but they are grouped together in a single object. Okay, that's something important you have to remember. You can't just say I want a bunch of different things. You have to group them together. So probably the most common way to group them is to either, well, I mean, these are probably the 2 most common, either combine them together using C, or to combine them together using a list. Okay, so if you want x, x squared, and x cubed, and in this case we named them, we can do that, okay? And it will return 2, 4, and 8, okay? And here I can throw in a vector, and it will run 2, 3, 4, 4, 9, 16, 8, 27, 64, and things like that, okay? And that's exactly what LM is doing. LM returns a single list, okay, full of all of these other stuff, full of the coefficients and the effects and the rank and the fitted values and all of that. It's there. It's just grouped together into a single list. Okay, when you create a function with multiple arguments, so a function can take in multiple values, and it's going to return one object. And so you can give it multiple values like x, y, and z, okay? And these are going to imply the names that are going to be used inside the function. So here I'm going to say I want to run f of 1, 2, 3, okay? So in this case, 1 gets matched up with the x, 2 gets matched up with the y, and 3 gets matched up with the z. The thing it's going to return is what paste 0 does, and it's going to do x is equal to, and x has the value 1, y has the value 2, and z has the value 3, and it returns this string, x is 1, y is 2, z is 3. And over here, because I have names, or I've named what these arguments are, I can say z is 1, x is 2, and y is 3, and then it's going to say, okay, x takes on the value 2, so when it runs paste 0, it's going to say x is, and it looks it up, 2, y is 3, and z is 1, and it returns that. X is 2, y is 3, z is 1. Okay? And likewise, if you name one of these things, y is 2, and you don't provide names for the others, it's going to try to match them up accordingly. Okay? And it'll do its best to try to figure out where these arguments should go. And if you give it some argument that doesn't exist, it'll throw an error. Sorry. And then you can also give it default values, just in case you're not sure if everyone's going to provide some things. So you have x is 1, y is 1, and z is 1 as default values. And so in this case, if I call f without any values provided, like whatever, it's going to just use x is 1, y is 1, and z is 1. Okay? And likewise, if I just provide it with 1, then it'll go to the first position, and it'll say x is 2, y 1, z 1. And here I can say z is 3, and x and y take on the default values, and z is 3. Things like that. Okay? Is that all right? All of this stuff? Okay, and again, use functions if you're about to copy and paste some code the third time, you definitely need to change it to a function. All right, we need to talk about scoping rules, okay? So R, as far as scoping goes, is it's generous in its scoping things, okay? So other languages, if you ask for the value of something and it doesn't exist in the current scope that you're working in, it's going to throw an error, okay? But R says, you know what? We're going to be forgiving. If I can't find it in my current scope, let's go searching for it until we do find it, okay? And what this means is that inside a function, this is not a good practice, but inside a function, you can reference values that have not been defined inside the function, okay? So you can imagine you're dealing inside this global environment, and when you run a function, it produces a local scope, okay? It produces a local environment, okay, like a little sandbox, and you're going to define values inside that thing. I'm going to go ahead and skip to this thing, okay? and the values that are produced inside this local scope while the function is running exist only while the function runs. Once the function is completed, it's going to poof disappear, and all values produced inside that scope go away, with the exception of the return value. The return value is the only thing that will remain, and that's the only way a function communicates with the kind of the outside world. Okay, and so if you did something like remove list equals ls inside the function, that will only delete the values that exist inside the scope of the function. Okay. So anyway, let's go here. In this thing, I've defined y equal to 1 in the global environment. Here, I create a function f, which is a function of x, and the value it's going to return is going to return the value x plus y. Okay, and so when I call f of 3, x has the value 3, and it says I need to return the value 3 plus y. And inside this sandbox, the only value that's defined is 3. X is 3. And it's going to say, I don't know what y is. Okay? So in other languages, this would produce an error. But in R says, well, you've asked for y. I don't see y inside my local scope. I'm going to go searching for y. So it goes outside the sandbox, and it looks in the global environment. It goes, oh, look, y is right there. Y has the value 1. So let's use that. Okay? And so it's going to return the value 3 plus 1, and it returns 4. Okay? Over here, I have a function. Okay, so in the global environment, y has the value 1. Okay? Inside the function, I define the value y, and I say y is equal to 2 inside this sandbox. And then I call g of 3. So when this runs, I go into my function, y has the value 2, and then I say, what is x plus y? Okay, so x has the value 3, and I says, I need to return 3 plus y, and I look inside my sandbox, and I go, oh, y has 2, so I'm going to do 3 plus 2, and I return the value 5. Okay, this value of 2 for y does not affect the value in the global environment where y is 1. So in the global environment, y is still 1. Inside this sandbox, y is the value 2. I return 3 plus 2. I return 5. In the global environment, y is still 1. Is that okay? So, this is how scoping works. Okay, R is generous in its scoping rules. It's just you have to understand the rules of scope in order for this to work. Okay, so it's forgiving. If you don't define something inside the function, it's going to go searching for it, and it'll work. Okay. So I have a couple of slides here. I only got through, well, I don't remember which one. I think I got through 34 in the last class, and so we'll have to probably have to wrap this up. I'll try to get through 34 in the next for you guys as well. Okay, so here I'm doing some examples that kind of highlight how our scoping rules work and how this superassignment operator works. Okay, so you encountered superassignment in your first homework assignment. Okay, and I just said what's the difference here, and so here are some concrete examples of how superassignment works. Okay, so in the global environment, x, y, and z take on the value 1. Okay, and inside the function f, okay, so inside the function f, there's a sandbox, and I create the value 2 for y. Okay, I say y is the value 2. And within the function f, there's another sandbox for g, for the function g, and inside that, I'm going to produce the value z is 3. Okay, so when f is executed, what happens is it runs the code for f, it produces y is 2, it defines the function g, but it actually doesn't care what g says yet. Okay, but it's only here when it says return what g returns, then it's going to execute g, it's going to search for z is, it's going to produce z is 3, and it needs to return the value x, y, and z, okay? So it's gonna search for x. It searches, so we're starting inside the sandbox, the tiny sandbox for G. It says there's no value of x. So it goes into the sandbox for F. And it says there's no value for x. So it goes to the global environment and says, oh, x is the value 1. So x is 1. Then it says we need the value of y. It searches G. There's no value of y. It searches F. It finds y is 2 inside F. So it's going to use 2. Then it goes to Z and it says we need the value of Z. Inside the tiniest environment for G, Z has the value 3. So it's going to return 1 plus 2 plus 3, and it returns the value 6. Out in the global environment, if I ask what's the value of x, y, and z, it's going to say 1, 1, and 1. Okay, because these values of x, y, and z are unaffected by these assignment operators here. Over here, I define x, y, and z in the global environment to be 1. And when f runs, okay, the only difference between the previous function and this function is I've used the super assignment here, okay? So when I run f, it's going to say, all right, let's look at the code inside f, okay? So f, we have the sandbox, and here it says assign the value 2, but super assign it to y. So when you do super assignment, it doesn't create a local value of y, it just says look for y in the higher scope. And so it goes to the global environment and it says, do I find a y? I did. I'm going to assign the value 2 there, okay? Even if y didn't exist in the global environment, it would create a value of y equal to 2 in the global environment, okay? Then inside, and then it creates G, but it doesn't actually care about G until it gets to this line that says return G. When it says return G, then it says, oh, now I've got to execute G. So we're inside the environment for F, and then it says I got to execute G. So it creates a new environment inside. So we have an environment for G, and inside G, the first line of code says super assign 3 to Z. So it starts off here, and then it says, okay, I'm going to search the higher scope for a value of Z. It doesn't find Z anywhere inside F, and so it says, okay, let's search the higher scope, and it goes to the global environment, and it finds a Z, and it changes the value of Z in the global environment to 3. Okay, and then now it says return x plus y plus z. So again, we're inside G. It searches for x. It's not there. It goes to F. It searches there. X is not there. It goes to the global environment. X has the value 1. Then it searches for y. It searches inside G. Y does not exist in G. It searches F. Does y exist inside F? It does not, okay? Because we super assigned 2 to y inside F. So it goes to the global environment and it finds y is the value 2. Then it goes for Z. It searches inside G for Z. Z does not exist there. It searches F. Z does not exist inside F. It searches the global environment and it finds Z takes on the value 3. So it returns 1 plus 2 plus 3, and we get 6. Okay? And if I ask now, what is the value of x, y, and z in the global environment, they have the values 1, 2, and 3. Right? Is the distinction between what happened in this function and what happened in this function, is that okay? Yes?
Can you repeat what happens if y wasn't declared in the global environment?
So even if I didn't have y or z in the global environment, the super assignment, what that will do is it'll start by searching the higher scope, and it keeps searching, and when if it finds it, it'll replace that value. If it doesn't find it, it goes all the way to the global environment, and if it doesn't find it in the global environment, it will just create it in the global environment. Okay? So here's one that's a little bit different, okay? I've got x, y, z defined as 1 in the global environment, okay? Now we've got the function f, okay? Function f creates a sandbox, and within this sandbox, I create a local value of 2 for y. And over here, I also do super assign 4 to y, okay? So when this code runs, the local value of 2 is y takes on the value 2 inside the f sandbox, okay? This thing, this super assignment will directly say, I want to change the value of y in the higher scope, which is the global environment, and that will take the value 4, okay? Then G runs, and it says, assign 3 to z, okay? It's going to search, so when it does this, it doesn't even start off in the local G. It goes immediately to F. It says, do I find a z there? No. So we go to the global, and it's going to assign the value 3 to z in the global. And then when it says return x, y, and z, it's going to look for x. It's not found in G. It's not found in F. And it finds the 1 in the global environment. Okay, when it looks for y, it first searches G. It's not there. It goes to the higher scope F, and F has a local value of y equal to 2. So it's going to use the value 2 here. And then it looks for z. Okay, and again, z doesn't exist in G, it doesn't exist in F, but it only exists in the global environment, and it has the value of 3. Okay, so it goes 1 plus 2 plus 3, and it returns 6. And then when we ask what is x, y, z in the global environment, the values are 1, 4, and 3. Okay. Is this okay? This is about as far as we got in the other class, so we'll also end here, and so that when we pick up on Monday, we'll keep discussing this topic. The first time you encounter these scoping rules, it's going to feel strange and weird, okay? But if you understand them, they make sense, and you'll understand how the scoping rules work in R. Okay, we'll stop, and we'll see you guys on Monday. Have a good weekend.